There is a echo. Please stop.
Bhatkar sir. Oh, mute. Hello. Ha.
Yeah, now it's okay.
Okay. Today, the Department of Mechanical Engineering, Student Chapter of Institution of Engineers and ISHRAE organized the expert lecture on modeling of two-phase frictional pressure gradient in refrigeration and air conditioning by Dr. Mohammad Awad, Associate Professor, Mansoura University, Mansoura, Egypt. These lectures will be useful for the researchers, engineers, faculties, and students. As we know, the cold chain need to increase worldwide to make up the market demands of agricultural products, etc. Also, to overcome the pandemic situations, the corona vaccine is invented, and it is also there is a need to store it at a lower temperature in cold storage. Our Indian government also takes the initiative and launched the India Cooling Action Plan to strengthen the research in the field of refrigeration and air conditioning. And all these efforts of by the government shows that in the near future, there are a lot of opportunities are created in this field for students as well as the researchers. So today's topic is more relevant towards the research in the field of two-phase modeling, which minimize the pressure gradient or pressure loss and power consumption in refrigeration industries. Now let me introduce today's expert and renowned scientist in the field of refrigeration and air conditioning, Dr. Mohammad Awad.
Good day, everyone.
It's
my okay.
Professor,
Okay.
I introduced. I will give your introductions. Then you will start after some introduction with the principal, sir. Dr. Mohammad Awad is an associate professor at Mechanical Power Engineering Department, Faculty of Engineering, Mansoura University, Mansoura, Egypt. He was a postdoctorate fellow in mechanical engineering in the Faculty of Engineering and Applied Science, Memorial University of Newfoundland, Canada. He received his PhD from Memorial University of Newfoundland in 2007 and his undergraduate degree and his master's degree from Mansoura University, Egypt in 1996 and 2000 respectively. His research focus is on the development of robust models for characterizing transport phenomena using fundamental theory. These models are validated using experimental and or numerical results. He is the author of 4 book chapters. He has published more than 100 papers in referred journals and conference proceedings in these areas. Presently, his research is focused on renewable energy, the modeling of complex fluid dynamics, heat transfer problems in internal flows. This includes transport in porous media, compact heat exchangers, two-phase flow in oil and gas operations, microchannel flows, non-Newtonian flows, and thermal design, optimization of energy systems. He is member of the American Society of Mechanical Engineers, ASME. He was also a recipient of the ASME International Petroleum Technology Institute IPTI Award in 2005 and 2006. He won silver medal at 45th International Exhibition of Inventions, Geneva, Swiss, between 29 March and 2nd April 2017. His patent was solar-powered portable apparatus for extracting water from air using desiccant solution. And in this field, he has done very much research. And whatever the particles, water particles in the air, that condensate is useful where there is a lack of water, the area where there is a lack of water. He was representative of Mansoura University in Research and Policy Committee members for the mega research project among MIT USA and 3 Egyptian universities, Ain Shams University, Mansoura University, and Aswan University between August 2019 and October 2022. So such a great personalities with us, and it is our privilege to hear the innovative thought from such a great personalities, which will be useful for the faculties and researchers also. Now, I request our head of department, Dr. Purandare sir, to brief about the department to everyone.
Good morning to today's honorable guest, Dr. Awad sir, and welcome for this session, which may call it is as an interaction of knowledge session. respected principal sir, Dr. Katari sir, Dr. Berger sir, all my colleagues, and dear student friends. Welcome to all for this session of interaction. Mechanical engineering department is accredited with NAC as well as NAC and A grade and MBA also. So due to this accreditation, our focus is very clear towards research, and we are moving in different fields of mechanical engineering in the form of grabbing higher and higher ups in the research and technology. So as a research initiative, we are organizing different type of sessions from the experts in this particular field so that student gets highlighted with these type of activities. So whatever things are going on in actual practice in the form of research as well as whatever practices are in the industries are there, these are always tried or these are always highlighted in front of students, and in this regards we are organizing series of lectures in this scenario. So in this, I am welcoming Dr. Muhammad Awad from Mansoura University for this session and highlighting us, because this is a very interesting topic in which we are able to do certain things in refrigeration and air conditioning, because whenever we are designing any type of system, always there might be certain amount of physical changes which are going on, and one of the physical change what we are having, that is nothing but the phase change. And this phase change is hampering not only on the process of heat transfer but also on the mechanical properties of the different aspects. So I'm very glad to hear the topic, which is very interesting to me, that is modeling of two-phase frictional pressure drop, because I'm a hardcore heat exchanger person who worked on the heat exchanger for my research work. So I'm welcoming Dr. Awad sir for this wonderful session which is going ahead. Over to you, Katari sir.
Thank you, sir. Today, the number of persons from the industries also joined this program. Number of researchers from other colleges, that is the government colleges, they are also joined this program. And now let me introduce our principal sir, Dr. S.M. Deshpande, to present their valuable thoughts, because we are looking forward towards the collaborations, international collaborations in the field of research, in the field of academics, and we are always ready for that one. And we are having also one of the center. That centers we set up with the Tata Technologies. Near about the 20 crore investment is there from management aid as well as the Tata Technologies. And it will be the good for the collaborations, and we are open for the foreign universities. So please, some things highlights we hear from the principal, sir.
Good morning, sir. For you, it is morning. For us, it is afternoon. Anyway, I'm really thankful and grateful to you for being with us for this particular session. Rather marching towards quality or maintaining quality, we are looking forward towards eminent personalities like you, who have worked really hard and really long into a particular field. This is one of the lectures in that particular series, and I would say we are very lucky and very fortunate to have you with us, sir. And of course, I have seen something like 110 plus participants in this particular meeting. I believe everybody will be greatly benefited from your wisdom, your knowledge, your sharing of what you have done, what projects you have handled, and I believe that will go a long way to enhance their knowledge, and hopefully this learning will continue in future, wherein everybody will be taking it to a next level, and maybe a joint research activities, joint collaborations. Maybe some students would like to come to your in university to have a look at what is taking place at your university, and vice versa. So hopefully this will come grow to a higher level or go to a next level, wherein all of us will be benefited. Thank you very much for your kind consideration of accepting our request. and giving us valuable time. With these words, again, I will hand over to Dr. Katari, who is the coordinator for this session. Thank you. Thank you, sir.
Thank you, sir. Now I request to Dr. Awad to present
Yes.
their views on the topics. The participants are requested to post their questions in the message box, and at the end of the lectures, after the end of the lectures, we will take the questions, necessary questions to discuss with the professor. And again, the professor will share their views and numbers and everything over there. So it will be beneficial for the participants. I request to Professor Awad, please.
So should I share my screen now?
Yeah. Now you have to share your screen, Professor.
Okay. So you can see my screen now? I share my screen. Can you see my screen?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Okay. Good day, everyone. Thank you for your invitation, and it's my pleasure to with you as a student, researcher, and people from industry. Today, my topic is about modeling of two-phase friction pressure gradient in refrigeration and air conditioning system. As said about me in the introduction, I have 4-book chapter, 3-book chapter with the publisher Intech, and it's published as open access. So as a student or a researcher or people from industry, please feel free to share this link that I will show in my next slide with the people, because you can download my this book chapter for free. And I have 1-book chapter with Elsevier, which was published last month in January 2021. My 3 chapter was in tech. It's the first one was published in 2012 about thermodynamic optimization in heat exchanger using entropy generation. My second chapter, which I will cover many items from this chapter in my talk today, is about two-phase flow. It's also published in 2012, and I have another chapter because, as you know, in refrigeration and air conditioning system, you can find the boiling and condensation process. So my third chapter, which was published in 2015, is about a critical review on condensation pressure drop in macro channel and mini channel. In this slide, I will show you an example how to you download my two-phase flow chapter, and you can use the same to download also in the same way my thermodynamic optimization chapter and my condensation pressure drop chapter. When you go to the chapter link, it's ask you about your information like first name, last name, your email. You can enter your institute email or personal your email. And in the field of research, you choose option physical science, energy, engineering, and technology. And in country, you select India, and select also please contact me when a new book and chapter are on related topic are published, so you be updated by any new chapter or book related to this area in engineering and technology. 2 days ago, I received this from the publisher that they told me my book chapter 2 phase flow has reached more than 11,000 download. And in the second photo, you can find the top 5 country where this download are coming. It's like United States of America, India, United Kingdom, China, and Egypt. So I am proud that your country is one of the top 5 country where download come to my shop. My last chapter, which was published last month, is like published in a book titled Design and Performance Optimization of Renewable Energy System. This is not open access, but you can enter Elsevier via your institution log on. Among 16 chapters in this book, my chapter is number 7. It's about like using parametric optimization for a solar solar water heat. I have like 5 co-authors from India. They are from different locations, such as Indian Institute of Technology in Bombay. And this is the link of the book. As said in the introduction, I hope at the end of my talk today, it's open a kind of international cooperation between my side and your side as a student, researcher, and the people from industry. For example, when I attended the 9th International Conference of Multi-Phase Flow about 5 years ago in Italy, one of the keynote speaker at this conference was Professor Omar Matar from the Department of Chemical Engineer at Imperial College London. During his talk, he said the next generation productive tools for multi-phase flow, we need an international collaboration. So now international collaboration between different countries, different institutes is very important. Today, this is the outline of my talk. I will give a brief introduction about two-phase flow application, different component of total pressure drop, and the different models that we use. Then I will give a short review about like model of two-phase friction pressure gradient and two-phase void fraction, because we need void fraction to calculate the acceleration component in boiling and condensation process. And during my talk, I will give 3 different methodology to predict the frictional pressure gradient in refrigeration and air conditioning systems. The first method will be using new properties of two-phase flow to use homogeneous model. The second method will be about asymptotic method in two-phase flow. The third method will be bounce in two-phase flow. And I will give some result discussion using available data in literature to validate this model. And at the end, I will give a summary of my talk and conclusion.
Professor, can you make a slideshow? It will be more visible to participants.
Just 1 minute. Means enlarge it.
Please press the button F5. I think so.
F5?
Yeah.
Just 1 minute.
Or in an option, there is a option of the slideshow.
Just 1 minute. I will try to.
If it is not, please continue. If it is not possible.
Just a minute. I am trying. Okay, I will continue. We can find the two-phase flow in many applications in our life, like petroleum industry, refrigeration and air condition, and the steam power plant. For example, as you know, refrigeration cycle consists of 4 different parts: evaporator, compressor, condenser, and expansion valve. We can find the two-phase flow, for example, in evaporator section. We can divide the total component of measured pressure drop into 3 components. The first component is frictional pressure drop. The second component is like acceleration pressure drop, and the third component is gravitational pressure drop. If like our device is in horizontal orientation, the gravitational component is equal to 0. Acceleration pressure drop, it's negligible in like adiabatic two-phase flow, but we in like our case today, like boiling and the condensation process, it has a value, and we calculate it in terms of void fraction. The void fraction is defined as a ratio of gas area to the total area of liquid and gas. In modeling two-phase flow in general, there is 2 basic model. The first model is like homogeneous model, and the second model is segregated flow model. In homogeneous model, we assume that both liquid and gas are move with the same velocity. So the slip ratio, which is can be defined as the ratio of average velocity of by gas to the average velocity by liquid, is approach 1. And I will use the homogeneous model in my first model today. The second model is like separated model. We assume that both liquid and the gas are moved separately, and we apply like continuity equation, momentum equation, and energy equation for each phase alone, and at the interface, like shear stress is equal, is equal, and the velocity is equal. And I will use separated flow model in my second method today. Today I am giving first a comprehensive review of different two-phase flow, frictional pressure gradient, and void friction model and their limitation. After that, I introduce the first method that I use in modeling, which like introducing new definition of two-phase flow viscosity to the field of two-phase flow. Then I introduced development of robust modeling to predict two-phase friction pressure gradient in circle pipes used as a methodological modeling method. And my last method is like I will develop lower and upper bound in two-phase flow pressure gradient as well and void fraction. I extend the third method also for like in case if I using like a small diameter, like the case of mini channel and the macro channel. Today I will start with covering like some previous work, and because you know in research when you try to develop new idea or some, you make first a survey in literature, and based on this survey you try to find a gap in literature so you can start your new idea. This model by Lockhart Martinelli was introduced more than 70 years ago in 1949. It was based on a graphical method. As we can show, the lower part of the graph is like for two-phase frictional pressure drop, and the upper part of the curve is like for void fraction, and which is user symbol alpha for void fraction, and the symbol 1 minus alpha means like ratio of area occupied by liquid to the total area. In this graph, the horizontal axis is capital X, capital where X square is defined like the ratio of pressure drop of single phase liquid to the pressure drop of single phase gas. And we have usually in literature we express frictional pressure drop in dimensionless form. In case of using homogeneous model, we use like friction factor, either Darcy friction factor or Fanning friction factor. For separated model, we use something called two-phase friction multiplier and has the symbol phi square. In this curve, we have like phi L square and phi G square. Phi L squared is defined by two-phase frictional pressure drop to single phase liquid pressure drop, and phi G square equal the ratio of two-phase frictional pressure drop to single phase gas pressure drop. You cannot see here in this curve there is 4 different curves. Why there is 4 different curves? Because there is 4 different scenarios for combination of liquid and gas. The first scenario is like if both liquid and the gas are in turbulent region. Turbulent region means like a value of Reynolds number for both liquid and gas phase are greater than 3000. And the second scenario is like if liquid phase is laminar while the gas phase is turbulent. And the third scenario is like when if liquid phase is turbulent while the gas phase is turbulent. And the third fourth case is like both liquid and the gas are laminar. Last case, for example, we can find both liquid and gas are laminar in a small diameter like mini channel and macro channel. Here we can note also from this figure as like with increasing capital X, phi L square is decrease with increasing X. For the curve of phi Lg square with increasing capital X, phi L square G is increased, and both phi L square and phi G squared are equal at capital X equal to 1. As an application for separated model, Turner in 1966 introduced one model called separated Slender model. In his assumption, he assumed that two-phase flow is independent of each other in horizontal separated parallel circle cylinder, and the cross-sectional area of the two cylinders add up to that the actual pipe. And the frictional pressure gradient in each imagined cylinder is the same as actual flow, and it's calculated using the single phase flow theory. And he put his model in this form 1 over phi L squared to power 1 over n plus 1 over phi Lg squared to power 1 over n is equal to 1. And he also introduced this model for void fraction. Alpha is equal 1 or in the numerator we have 1, in the denominator we have 1 plus x to power 2 over n, and he give value to n for different scenario. For example, if like both liquid and gas are laminar, n is equal to 2. If like, for example, both liquid and gas are turbulent, n is equal to 4. The model that was introduced in 1949 by Lockhart and Martinelli. The graph that I showed a few minutes before shows Holm in 1967 try to use like computer modeling to express this graph in form of equation. His equation is consists of 3 terms, for example, and the only unknown parameter is capital C. C is defined as a chosen parameter, and for example, the equation of phi L square is equal 1 plus C over X plus 1 over X square, and phi G square equal 1 plus C times X plus X square. For example, if like both liquid and gas is turbulent, C is equal to 20. If like gas is turbulent while if liquid is turbulent while gas is laminar, C is equal to 12. If like liquid is laminar while gas is turbulent, C is equal to 10. And if both liquid and gas is laminar, C is equal to 5. Also, the same researcher develop another more complex correlation based on Berger plot in 1973, and this model is function of like the different parameter like gamma, which is physical property ratio, and x small is like the Reynolds fraction, and B is function of like gas flux, which is mass flow rate per unit area. In 1979, using like curve fitting of that set of consists of like to 25,000 data point, this correlation is developed as a function of different parameters like Weber number, Froude number, and dimensionless number like F and H, and this definition is here. Like in some researcher from Germany, Mueller and Heck, in 1996 developed also a correlation for pressure drop, where the equation appears in this 2 slides. When I previous model, when I compare this previous model for the case like of refrigerant 12 in a pipe diameter equal 10 millimeter at the Reynolds fraction equal 0.5 and the saturation temperature equal 15 degrees Celsius, we find like each model give a different prediction. So the chosen model gives the highest prediction, while the Mueller Heck gives the lowest prediction. Now I will introduce some previous model for calculating or predict void fraction, because we need the void fraction to calculate the acceleration pressure drop which exists in like boiling and condensation process. Zephy in 1975 used like the concept of minimum entropy production to develop void fraction as function of the Reynolds fraction liquid density and vapor density. His model was successful to predict pressure drop and heat transfer during condensation. In the same year, Tom developed a void fraction correlation for steam water in terms of two variables: slip ratio and mass quality. From this equation, we can density ratio approach 1 near the critical point is approach 1 and void fraction equal to x. For example, if you substitute s equal to 1, then from this equation you can find alpha is equal to small x. 1 year later, Brochi developed a correlation, but in graphical method, in terms of like viscosity ratio and the density ratio. His correlation was like for in terms also in Lockhart-Martinelli parameter. Chisholm developed a correlation in 1972 to predict void fraction in terms of slip ratio x and the density ratio, and he find his correlation gave accurate result, although his correlation is very simple. When I try to compare the previous model for the case of refrigerant R22 in pipe diameter of 10 millimeter at the saturation temperature of like 50 Celsius, I find the both model, all model give different value. Of course, at x equal 0, alpha equals 0, and at x equal 1, alpha equals to 1. And now I will start give a brief introduction of more the 3 different methods that I will cover in my talk today. The first method will introducing a new definition of two-phase viscosity that we can use in homogeneous model approach. The second method will be using a asymptotic modeling approach for with separated modeled flow. And finally, I will introduce development of bounds for experimental data for pressure gradient and void fraction. I introduced first method in 2006, and for this idea, as said about me in the introduction, I obtained like 2 awards from International Petroleum Technology Institute, American Society of Mechanical Engineering in 2005 and 2006. For this idea, I obtained the award in 2006. Basically, I make analogy between like thermal conductivity in porous media and the viscosity in two-phase flow, and I use the following assumption. Like homogeneous mixture is there is an analogy between two-phase flow mixture and thermal conductivity of porous media. There is an analogy between like liquid viscosity and K1. There is an analogy between gas viscosity and K2, and there is an analogy between mass fraction X and V2. And in these two cases, from this plot, we have like the series definition is we have a similar definition of two-phase viscosity, which I show later, and we have parallel definition of two-phase viscosity. So the between the lower curve and the upper curve, this three curve by introducing a new definition of two-phase viscosity. And this is the equation of two-phase viscosity. It's first equation, second equation, third equation. Later, when I published this paper in 2008 as a journal paper, I combined the first definition and second definition using like arithmetic mean average. All of this definition satisfy two important condition. When mass flux approach zero, which means that all flow is liquid, viscosity of mixture is equal to viscosity of liquid. On the other hand, when like mass quality approach 1, which means that all flow is vapor, viscosity of mixture is equal to viscosity of gas. I try to validate this three definition using data for circular pipe and data for middle channel and macro channel. Usually in for like circular pipe, the flow is turbulent, so I use the equation of like friction factor is equal 0.079 over Reynolds to power 1/4. And I find like my new definition give a good prediction with the lowest root mean square error value. For like a small diameter, like the case of mini channel and macro channel, I defined the use definition of Churchill, which to cover like model charted diagram to cover like this equation has different advantage. For example, it cover like laminar region, transition region between laminar and turbulent turbulent region. Also take into account roughness if like flow is moving in roughness pipe, not smooth pipe. And also my new definition give the lowest root mean square error value. And in this table, sorry, I in this table, before I introduce my second method, which it's related to like asymptotic approach, the Turner model, which introduced in 1966, I make a like general model for different scenario. Where M and N, as you know, in like for example, in laminar flow, fanning friction factor is equal to 16 over Reynolds number. So M means like exponent of Reynolds number in the denominator. On the other hand, if like flow is turbulent, fanning friction factor is defined by 0.079 over to Reynolds to power 1/4. So n, for example, n equal to 0.25 represent the turbulent flow. And also in the last column, this is the value for void fraction in terms of Lockhart-Martinelli parameter. Next slide, I show like phi L and phi G versus Lockhart-Martinelli parameter, and 1 over L and 1 over phi, 1 over alpha and alpha versus Lockhart-Martinelli parameter for different value of M and L, for different value of M and N. Social and Usagi has a very famous paper in 1972 about like asymptotic model approach. Asymptotic model approach, we can apply it in different engineering area, such as two-phase flow, fluid mechanics, heat transfer, and energy. For example, I have one comment paper in applied thermal engineering that was published in December 2019. It's like comment on experimental study of thermal hydraulic performance of woven fin and flat tube aluminum heat exchange. And this is the link of my paper. In this paper, I mentioned more than like 15 references that based on my publication of asymptotic model in different area, like two-phase flow in circular pipe, two-phase flow in main channel and macro channel, two-phase flow in porous media, two-phase flow in fracture, and so on. Two-phase flow of, heat transfer in like woven fin heat exchanger, and so on. So you can, if you interested to know more about this application, you can download this reference, because due to time limitation, I can't cover all of this application today in my talk. In asymptotic model, as shown in this curve like relation between dependent parameter and independent parameter, from this equation the only unknown is B. So one major advantage of asymptotic models, it has only one unknown, and we determine this unknown by solving like nonlinear equation near the intersection of these two asymptotes. For example, we have like in this plot we have two dashed line, which like represent asymptote at high value of x-axis and this asymptote at a high value of x-axis, and we can obtain this near the intersection of two dashed line. We try to obtain this value of y-axis either from numerical data or experimental data, or we can, for example, carry our own experiment. For in two-phase flow using separate flow model, the equation using asymptotic model has this form. Like first, I write the form in terms of like frictional pressure gradient, and then I transfer it in non-dimensionless form, either using two-phase friction multiplier for liquid phase or two-phase friction multiplier for gas phase as a function of Lockhart-Martinelli parameter. And as shown in this equation, the only parameter is B. There is a special case if like linear superposition, the exponent B is equal to 1. For example, if in this equation, if I substitute B is equal to 1, the physical meaning is like two-phase friction multiplication gradient is the sum of liquid phase pressure drop plus gas phase pressure drop. Here I put the equation like either using Churchill model to cover all the area like laminar transition and turbulent, and taking into account the roughness effect. In my next slide, I present like compare asymptotic model with published data by Duckler in 1964, and the value B is equal 1/4. And in this table, I put like asymptotic model with previous models that I showed today in the literature, such as Chisholm and Friedel. And you can, from this table, you can notice that my present model has the lowest root mean square model. Also, I compare this model in terms of like dimensionless form, either in terms of phi L versus X, or as shown in this slide, using different different data point from literature, or as shown in next slide in terms of phi G versus Lockhart-Martinelli parameter. And in this table, I summarize the root mean square error for like different data set. Here we, for example, you can notice that, for example, for the Duckler data is B is equal to 3.9. For Chisholm data, B is equal to 4. And so I try to make like use one value of B, because B, for example, in this table changes from 2.8 to 4. So I take almost B as 3.25 in case of like a circular pipe. And for a small diameter like mini channel and macro channel, I find that the range of B from like 1.55 to 2.55. So I take average value of B as 2. And my last method that I will cover today is like about, I try to develop lower bound and the upper bound. So almost all the experimental data fill the area between upper bound and lower bound. The bound approach is very useful in design and analysis as an engineer to use the resulting average and the bound value and predictions the system performance. Average bound means like arithmetic mean, which like upper mean value plus lower mean value divided by 2. The bound approach is also useful when conducting new experiment, since it provides a reasonable envelope for the data to fill within. The bound are providing us the most realistic range of data and not firm absolute limit. In this slide, I develop like lower bound and upper bound for like two-phase flow friction multiplier and larger circle diameter And during develop this model, I assume that both liquid and gas are in turbulent region. In using the same assumption, also, I success to develop a fraction. On the other hand, in a small diameter case like minute channel and the minute channel, I develop like bounds for frictional pressure drop. But in this case, I use the assumption like both liquid and the gas are in turbulent, in laminar region, which means that Reynolds number for both liquid and the gas is less than 2000. As I mentioned, for example, if in this lower equation, if you compare it with the Chisholm form that he introduced in 1967, this means that C is equal to 0, which means that there is no interaction between the liquid phase and the gas phase. For example, the upper bound, it's like C equal to 5, which means like the equation for laminar liquid laminar gas flow. And as you notice, like the average of 0 and 5 is 2.5, so this is the equation of the mean. Here I try to present some data to validate my model. For example, this data is like Furion like 22 and diameter of like 10 millimeter and saturation temperature of 50 Celsius. Also, I try to introduce like validation of this model in terms of like dimensionless form, either for phi L versus Lockhart-Martinelli parameter or phi G versus Lockhart-Martinelli parameter. And I have a good value of like root mean square error, which for example around like 15%, which is good in the field of two-phase flow. Also, as I mentioned, it's important to know the value of a void fraction, because we need the void fraction to calculate the acceleration pressure drop in boiling and condensation process. So here I introduced like equation for lower bound and upper bound for a circular pipe, and I try to compare this equation for using a different data set of refrigerant 12 and refrigerant 22. Sometimes data is available in literature for like liquid void fraction, which means 1 minus alpha. So I also compare here, for example, in this plot, 1 minus alpha versus x. As a summary on conclusion of my talk today, I show new definition of two-phase flow that we can use to calculate two-phase friction pressure drop using the homogeneous model. Also, I introduce application of the asymptotic model in the field of two-phase flow, and the comparison of the asymptotic model with experimental data show good agreement. And the last model that I show today is like bound model, which is very useful in bounding the two-phase parameter for different working fluid over a wide range of variables such as mass flux, mass quality, pipe diameter, and saturation temperature. and the proposed mean model, which is a arithmetic average of lower bound and upper bound, can provide excellent prediction of two-phase flow parameter. This research either I did in Canada or after I returned back in 2009 to Egypt, was funded by a different organization, for example, such as Natural Science and Engineering Research Council of Canada. Also, I acknowledge American Society of Mechanical Engineering and International Petroleum Technology Institute, because they gave me scholarship in 2005 and 2006. And I mentioned this acknowledgement at the end of my book chapter, Two-Phase Flow. During my postdoctoral, when I apply like two-phase flow in oil and gas industry, like porous media and oil and gas, this research was funded by Petro Canada Young Innovator Program and Atlantic Innovation Fund, because my university in Canada, Memorial University, in Canada, is located in the east coast of Canada. Actually, St. John's, the city of my university, is like an island in Atlantic Ocean. On the other hand, the west coast of Canada is located at the Pacific Ocean. And due to time limitation, because I know that I have almost 1 hour, I mention here my contact information, my university email, and my personal email, and my WhatsApp. So either a student or a faculty member or the people from industry or ISHRAE, it's welcome to send me any question or any suggestion for a joint work as a future cooperation among us. And again, thank you very much for giving me this chance to be with you today. And I hope that my talk is interesting to you. Thank you.
Thank you, sir. Your lecture was very nice for all our students. Our one undergraduate student, Mr. Sahil Barsikar, want to ask one question.
Yes.
So his question is, how do you proceed in solving research problems and approach in multi-phase flows?
Actually, in multi-phase flow, there is different approach. For example, I can use experimental and now these days we have like modern technology. For example, we have like, can take some photographs, IV system and so on. There is also the people are using like numerical technique, using like different solver, either like some package like in CFD, some package like ANSYS, or some package like OpenFOAM. And actually, I benefit from the experience of my PhD advisor, Professor Mazoshka, because he obtained his PhD in like heat exchanger at low Reynolds number. And during his PhD, he applied like some methods that I introduced today, like asymptotic method. So the methods that he applied in his PhD, I tried to, in field of heat exchanger, I try to apply it like in two-phase flow. And there is a different technique. For example, if you download my book chapter, I mention about like 10 different methods to model two-phase flow problem. For example, one of the methods that I have like 3 publication on it, 2 journal paper and 1 conference paper that I presented in like international conference on multi-phase flow in Italy in 2016 about like artificial neural network application. What you try to, like to obtain data set either from your experiment, from literature, from published work, and model like, for example, you predict void fraction as in terms of different parameter like liquid velocity, gas velocity, uh, sorry, liquid velocity, sorry, liquid viscosity, liquid density, gas density, gas viscosity. So depending in like in which as we say all ways lead to Rome, but for example about myself I prefer like to deal with the problem analytically. Other people like to develop the problem and solve it experiment. For example, I have also during my master thesis in Egypt before that I finished in 2000 before I traveled to Canada in 2002. I deal with like thermosiphon. Thermosiphon, if some people doesn't know it, it consists of like 3 parts: evaporator part, where the evaporation occurs, then adiabatic section which is separate evaporator, and the last part and condensation where the working fluid condensate and return back to the evaporator by gravity. During my master thesis in Egypt, I studied the different parameter like such as filling ratio, which is like volume of working fluid to that volume of the evaporator, and like heat flux and inclination angle on the performance of thermosiphon device. And I try to develop a correlation based on this experiment that I carried out during my master. So depend on the tools that you have, and depend like because some people are expert in like numerical, some people are expert in like in experiment, some people are expert in like analytical. But and it's but as you grow up in the field, you will have experience on almost many different methods to deal with the problem. And
can I ask second question?
And if you have any question, personal email, and this is my WhatsApp.
Okay.
You can ask me, and I will be happy to give you more details. And for example, if you are interested, I can send you like more publication related like different method to deal with two-phase flow modeling, such as artificial network and so on.
Okay. So second question I will asking you. So this is from my friend Pankaj Anjankar, and he is asking, what is
Yes.
the better approach to calculate friction factor, homogeneous mixture model or separate flow model? This is first question. He has put in the chat box.
If I okay, I will just let me return back.
Okay, he has put in the chat box.
I will return back to show one slide to answer this question.
Okay.
Just 1 minute.
Okay.
I am with you, but I am looking for the slide that has the figure and equation. Just 1 minute. Okay, actually the figure in one slide and the equation in one slide, so I will show both of them. From my point of view, the best equation that we use to predict for calculating the friction factor is like Churchill model. As shown in this plot, it covers like laminar region, transition region, and the turbulent region. Actually, this is his idea is like to express like a model chart that was introduced in like 1944 in terms of equation, and his equation also has another advantage of you dealing with flow in pipe with roughness. You can take roughness effect into account also. The equation of his model is shown in this slide. Just 1 minute. Okay, and this is the equation. His equation for fanning friction factor in terms of two constant A and B, and this is the equation of how to calculate the constant A and constant B. We cannot say as that constant B is function of Reynolds number, while constant A is function of Reynolds number and roughness. What I wanted to show here, his equation is valid only for like circular pipe. As you know, if in like fluid mechanics and heat transfer, if we deal with like fluid non-circular pipe like rectangular, triangular, square duct, and so on, we use something called the hydraulic diameter, which is calculated as like 4 times the cross-sectional area divided by weight parameter. You cannot see here the constant in this equation. The constant 8 actually is which represent 16 over 2. If you remember, for laminar flow in circular pipe, friction factor is equal 16 over Reynolds. But for example, if shape is not circular, this constant value is different. For example, for the case of square duct in laminar region, friction factor is equal 14.23 divided by Reynolds number. And in my book chapter that I show at the beginning of my talk, that how you can download it, I cover the different model for calculating friction factor. Also, I show how to calculate friction factor equation for different shape. For example, in the book Shah and London about heat exchanger, in which published in 1978, there is one famous correlation to calculate friction factor as a function of Reynolds number and aspect ratio for rectangular shape. Actually, my PhD advisor was thinking in extending Churchill model for to a non-circular shape by changing, like for example, but in this case, the constant 8 will be changed. Also, actually, I have also, but I didn't introduce this data today. I use this model in for like pipes with a roughness value, and this model gives good prediction. As you notice from my talk today, like for example, like 70 or 60 years ago, their computer was at the beginning, so the people was depending, like Modi was depending on bullet and to give the value. But later, when there is an advance in computer, people try to use like equation or as for example Chisholm in 1967 developed equation for Lockhart-Martinell parameter that appeared in 1949. One last note regarding like friction factor and Reynolds number. My PhD advisor during his PhD in low Reynolds number heat exchanger at the University of Waterloo, he developed like a new form for calculating hydraulic diameter in case of Lama Reynolds number. He shows that instead of using hydraulic diameter for non-circular shape, we can define the hydraulic diameter as the square root of the cross-sectional area. And based on his definition of using like hydraulic diameter as a square root of cross-section area instead of like the normal definition, which 4 times cross-sectional area divided by unit parameter, he obtained like a good prediction for data of heat exchanger at low Reynolds number. If you are interested of like using or have a look of some of my PhD advisor publication related to heat exchanger using the square root of cross-section area as a hydraulic diameter, I can send you this publication. Just email me.
Okay, thank you very much, Professor. We are having many queries in the chat box, but we will send you directly by email to you so that we can answer them.
Okay.
Yes, sir. It was very nice lecture and completely on the pressure drop and mini channels, micro channels, and it was very nice to you, we us. Myself, Dr. Vijay Bhatkar, ISHRAE Pune Chapter Student Chair, thankful to Dr. Mohammad M. Awad sir, Associate Professor, Mechanical Power Engineering Department, Mansoura University, Egypt, for delivering lecture on modeling of two-phase frictional pressure gradient in refrigeration and air conditioning systems. I am thankful to our principal sir, Dr. S.M. Deshpande sir, our HOD, Dr. P.S. Purandare sir, all HODs, deans, all faculty members, and our dear students. Special thanks to Dr. P.K. Katare sir, faculty advisor of Institution of Engineers, Student Chapter, and Professor Gaurav Chaudhary for organizing this lecture. I am thankful to ISHRAE President, Mr. Deepak Wani sir, and all CWC members and faculty advisors of ISHRAE Student Chapters and all student members. So thank you once again to one and all for attending this lecture. So,
okay, thank you, Professor. Thank you.
Thank you for your invitation. It's my pleasure to with you today. And
yeah,
I'm like a cooperation between us, because as I mentioned in my talk today, my last chapter which published in Elsevier about optimization for a solar air water heater was like with people from India. So I hope that it will be cooperation between me and your researcher and your people from industry in different area like refrigeration, air condition, heat exchanger, and so on.
Yeah, thanks. Let me see the good collaboration in future, and we will be contacting with you. So thank you. Can you please start your webcam? Camera.
Okay. Just 1 minute. I start my webcam, yes. You didn't see me?
Yeah. Now visible. Just take one snapshot from our side. So it is the memory with us. So
okay.
Okay. Thank you, Professor. Thank you.
Thank you. And this is a start of cooperation between us.
Okay.
Thank you.
Okay. Thank you.
Goodbye.
Good morning. Thank you.
Thank you.
Thank you. So now others can leave the meeting. Thank you for attending the lectures. पंकज अंजनकर आहेत का? अंजनकर सोडला. ठीक आहे, बंद करतो सर.